In this series of videos, we'll talk about a related group of reactions called electrophilic aromatic substitution reactions. These, in some ways, are similar to substitution reactions that we're already familiar with, but in a lot of ways they're different. And that's partly because the kinds of compounds that undergo electrophilic aromatic substitution reactions are aromatic compounds, and we already know that aromatic compounds are extremely stable compounds, and thus we need some tricks to induce them to undergo chemical reactions. So in this video we'll talk about what is electrophilic aromatic substitution, and then we'll go over three very classic examples of electrophilic aromatic substitution. Okay, so we've already said that if you have an isolated double bond, right, this is an isolated double bond, it's not conjugated, this is not an aromatic compound. These undergo addition reactions with things like bromine to give the anti-dibromide. One bromine is up and one bromine is down. But we've also said that benzene, because it's aromatic, because it has extreme stability associated with aromaticity, it won't react with bromine. It won't undergo, at least it won't undergo an addition reaction. It won't undergo any reaction unless we add a catalyst. But if we do add a catalyst, what we observe is not addition. We observe a substitution reaction, and this is different than the kinds of substitution reactions that we've seen before, because what we're doing is we're substituting a carbon-hydrogen bond for a carbon-bromine bond in the presence of an iron catalyst, plus we get HBr as a byproduct. So we've substituted a CH bond, which we haven't seen hydrogen as a leaving group before. In this case, it's not technically a leaving group. We'll see when we go over the mechanism exactly what is happening to that hydrogen. So we need a catalyst in order to induce benzene to undergo electrophilic aromatic substitution. That makes sense, right? Because benzene is extremely unreactive, and so we need to increase the reactivity of our electrophile. So how do we do that? How do we increase the reactivity of bromine? How do we make bromine more reactive? Well, the way we do that is we add a catalyst, and usually it's not iron. Usually it's iron tribromide, and but before I show you that, I want to go over some of the reactions that we'll talk about in this video. We'll talk about halogenation, mostly bromination and chlorination. We'll talk about nitration of benzene, and we'll talk about sulfonylation. In the next video, we'll talk about how we form new bonds to carbon-containing groups like alkyl and acyl groups in the next video by a reaction called the Friedel-Crafts reaction. Okay, so if we want to look at how we activate an electrophile, we want to make bromine into an electrophile, because what's happening in electrophilic aromatic substitution is benzene has these electron clouds that can be induced to attack something that's positively charged, right? So we need a really strong electrophile in order to attract the electrons from benzene. How do we do that? Well, we take bromine and we react it with a Lewis acid. Usually it's going to be iron tribromide or aluminum tribromide. And these are really good Lewis acids, remember, because they lack an octet of electrons. So they have an empty p orbital that can accept a pair of electrons to give them a full octet. So what happens is bromine, Br2, takes one of its lone pairs of electrons and attacks the Lewis acid to generate a Lewis acid-Lewis base complex, which can then lose the sigma bond to generate a Br+, which is much more electrophilic than neutral bromine. Now we have a formal positive charge on bromine. It's way more reactive, and now the electrons from benzene can be induced to attack it. So let's show that on the next slide. So let's say we have benzene. Our overall reaction is benzene reacts with bromine and iron tribromide to give bromobenzene. So how does that reaction work? Well, we just saw in the previous slide that combining these two things, we know the mechanism creates Br+, right? So in the first step, once we have Br+, we have 3 lone pairs on here. Any of these 3 double bonds can attack Br+, and then what we get is what we call a sigma complex, where if I draw out the hydrogen that's here, we have The hydrogen is still bonded, and the bromine is bonded. We have a hydrogen here, but we broke the pi bond, so we have a positive charge on this carbon, right? So this carbon's only making 3 bonds, this carbon's making 4 bonds. So we have sp2, 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 sp3. So we start with an aromatic compound, but this compound is not aromatic because we broke aromaticity to attack our really strongly activated electrophile, right? This compound has several resonance structures that I'm not going to worry about drawing right now. Those are going to be important later though. And then what happens is this compound is unstable, right? What could happen is a Br minus could attack here, right? But then we wouldn't be creating a more stable compound. We need to restore aromaticity to restore the stability associated with this compound. So now what happens is the Fe the iron bromide complex that we generated can abstract hydrogen. We should probably show this coming from the bond, because now what happens is we regenerate our catalyst, so we have FeBr3 plus HBr, right? And so that's how we lose this hydrogen. It gets deprotonated by this base. These 2 electrons are restored as a pi bond, so we go from an aromatic compound to an aromatic compound. That way we don't lose the stability associated with aromaticity. Okay, so if we draw a potential energy diagram, right, we start with benzene, which is very stable, it's aromatic, right? We get to our sigma complex, which I drew on the other slide. It's not aromatic, right, so it's not very stable, or it's not as stable as benzene, right? If we did an addition reaction, we would be going uphill in energy, right, because we lost aromaticity. So instead we remove the hydrogen, we drop down, and actually we get something that's more stable than what we started with because the carbon-hydrogen bond is weaker than the carbon-bromine bond. So from a thermodynamic perspective, it's an exothermic reaction or a favorable reaction. Okay, so what I said before, if we want to look at all the possibilities for halogenation, what we're going to talk about primarily is bromination and chlorination, and you can use aluminum tribromide or iron tribromide interchangeably. Either one will give you the same result, or you can use aluminum trichloride or iron trichloride as your Lewis acid. These are favorable reactions and can give you good yields of these halogenated benzene rings. Okay. So the mechanism that we're going to see for all electrophilic aromatic substitutions, it doesn't matter if you're doing halogenation or nitration or sulfonylation or anything, what happens is you generate, the trick for every electrophilic aromatic substitution is generating this extremely strong electrophile. But once that's generated, right, the electrons from benzene are induced to attack that electrophile to generate a sigma complex. And notice that this carbocation is allylic, so it has several resonance structures, but eventually a base is going to come along, pull off the hydrogen to restore aromaticity. So the net result is that we've substituted a carbon-hydrogen bond for a carbon-electrophile bond, and thus the name electrophilic aromatic substitution, you're substituting a CH bond for bond to your electrophile on an aromatic compound. Okay, so let's talk about some other electrophilic aromatic substitutions. Sulfonylation usually requires fuming sulfuric acid. Fuming is kind of confusing. It just means that you have sulfur trioxide dissolved in sulfuric acid. So it's a combination of sulfur trioxide and sulfuric acid that gives you this compound, which is called a sulfonic acid. So how does this reaction work? Well, let's think about what we said on the previous slide. So we have benzene, right? And the strong electrophile in this reaction that we actually don't have to generate in this one case is sulfur trioxide, which makes sense, right? It's a sulfur that's bonded to 3 electronegative oxygens. So this sulfur is really, really, really reactive and very positively charged because it has 3 electronegative atoms pulling electrons away from it. So just like in the other reactions that we've talked about, the electrons from the pi bond, from a pi bond of benzene attack the sulfur atom, and we break one of the 3 sulfur oxygen pi bonds, so we get our sigma complex just like we did in the other reaction. So we have a hydrogen here We have a sulfur and it's double bonded to oxygen, double bonded to oxygen. We have an O minus. We have a plus charge on this carbon, right? And then what can happen is that we lose a proton. So a base comes along, pulls off this proton, and it's probably the O minus from another molecule, right? So I'm just going to draw this being lost. So now what we have is we restored aromaticity, but we have a negative charge on our oxygen. We're in an extremely acidic environment, right? We have sulfuric acid, and we just generated another equivalent of acid. So some source of protons will protonate our oxygen to give us the final product, which is our sulfonic acid. So this is a relatively straightforward reaction. We attack sulfur trioxide, we lose a proton, and we protonate the oxygen to give us our sulfonic acid. Sulfonic acids are useful, and we'll talk about this in a later video when we talk about strategy, because you can put them off and take them, you can put them on and take them off under relatively mild conditions. So if you use concentrated fuming sulfuric acid, so no water present, then the equilibrium favors the sulfonic acid. If you add water and sulfuric acid, then you go back the other way and you can remove sulfonic acids. The last reaction we'll talk about in this video is nitration, and this involves mixing together two very strong acids, nitric acid and sulfuric acid, to nitrate benzene rings. This is extremely common and important reaction in organic chemistry. So the mechanism here, first we have to show how we generate our electrophile, right? We have nitric acid. So this is a Lewis dot structure for nitric acid, right? What we're going to do is react nitric acid with an even stronger acid. Sulfuric acid is much stronger than nitric acid. And so actually what happens is nitric acid in this reaction acts like a base, sulfuric acid acts like an acid, and just like we've seen in other examples, right, we're going to turn our OH from a bad leaving group into a good one. So we're going to protonate the oxygen with sulfuric acid. So we get something that looks like this. Okay. Now we've generated a good leaving group. So what happens is, at the same time that our leaving group leaves, we form another nitrogen-oxygen double bond. So our electrophile looks like this. We have a nitrogen, double bond to oxygen, double bond to oxygen with a positive charge. This is called the nitronium ion, which is an extremely strong electrophile. The nitrogen, again, has a formal positive charge and is bonded to two very electronegative oxygen atoms, so it really, really wants some electrons. It's very positively charged, right? So once we generate the nitronium ion, okay, then let's show how it gets attacked by benzene. It's exactly the same mechanism as we've seen in the other reactions, right? We have benzene. We have a very strong electrophile here. The nitronium ion is our electrophile. So benzene attacks nitrogen, and we break one of our nitrogen-oxygen double bonds. So we get our sigma complex. And then loss of a proton. So just these two electrons become the pi bond. We lose H+. So we have nitrobenzene plus a proton. We generated water in the previous step, so maybe water is our base in this reaction. If you want to show the base, you can. So in this case, the other product would be H3O+. So that's the mechanism. And remember, notice that there's a common mechanism that is occurring throughout. It's just the difference is what the electrophile is. But we have benzene attacks the electrophile, loss of a proton to restore aromaticity, the end, 2 steps. Okay, the last thing I want to talk about is what are nitro compounds useful for? Well, one thing that they're useful for is making anilines, We can reduce nitro groups to anilines or amine groups by using reducing conditions, either iron and HCl or zinc and HCl. So the two-step synthesis, if you want to make an aniline, is you nitrate in step 1 and then you reduce the nitro group in step 2 to get an NH2 group there. So to summarize, electrophilic aromatic substitution is a reaction where benzene undergoes substitution with extremely strong electrophiles to replace a CH bond with a new carbon bond to a different atom. It could be bromine, chlorine, sulfur, or nitrogen, as we've talked about in this video. Substitution is thermodynamically favorable, but you need to undergo substitution and not addition in order to keep aromaticity, in order to keep the stability associated with aromaticity. And we need extremely reactive electrophiles. So what we've talked about in this video is halogens activated by strong Lewis acids, sulfur trioxide, and the nitronium ion.